Since 2017, Andrew has served as editor-in-chief of the communications of the ACM, and he currently serves on the National Science Foundation SCI's Advisory Committee. Professor Chien leads the Zero Carbon Cloud project, exploring synergies between cloud computing and the renewable power grid. He is a global research leader in parallel computing, computer architecture, clusters, and cloud computing, and has received numerous awards for his research. Dr. Chien has served as Vice President of Research at Intel Corporation from 2005 to 2010, leading long-range and disruptive technologies research, as well as worldwide academic and government partnerships. Andrew is an ACM, IEEE, and AAAS Fellow, and earned his PhD, MS, and BS from MIT. Today, he is here to present his talk entitled "Cloud Computing is Becoming Carbon Aware. Can it become a zero carbon cloud?" With that, Andrew, thank you. You have the floor.
Can you guys hear me?
Sounds great.
Great. Thanks so much, Chandra. It's a pleasure to be here. I appreciate being invited to come and talk. And, I'm hoping that this talk will actually, spur some interest and excitement around some new problems that I think are facing the systems community and the architecture community. That's my ambition here. I hope to take advantage of giving a keynote to talk about that. It's really fun to come and talk about this topic because we really started, off in the wilderness, as shown in this upper left picture, right? We had this idea that computing should be synergistic with renewable energy way back in 2015. And back then it was just a smattering in an idea, like a professor's idea. But now it's coming to reality. Industrial organizations broke ground on the first types of these facilities in 2020, and I'll share some news a little bit later in the talk about some of the exciting large-scale things that are starting to happen. So I think that it's super gratifying, right? It's most gratifying for us as academics when some idea that we had actually comes into large-scale adoption and play. Okay, so I'm going to talk a little bit about why we care about this, what the problem is. And then I'm going to talk about this idea of good, better, best, because I think a lot of us struggle with this question of what should we really expect of computing and what should we really expect computing to do to help solve some of these sustainability problems, and how much is enough. And by the way, the corporate folks always want to do as little as possible. That's sort of the honest truth. So I'm going to talk about this zero carbon cloud idea, this computing infrastructure that we designed and demonstrated can accelerate decarbonization of the power grid. And then I'm going to close with maybe 5 or 10 minutes on talking about new opportunities that this poses in terms of systems and architecture research. And I'd be happy to take questions at the end. So the beginning of this story starts with something called Jevons paradox. And it has to do with this notion that a lot of times technologists spend their time thinking microscopically, when in fact the things that change the world are macroscopic effects. So Jevons is an economist in England in the 19th century, and he was asked to answer the question, what happens if we increase the efficiency of burning coal or processing coal? And he discovered, right, because in his economist, this notion called elastic demand. That is, if you reduce the cost of something, you increase its use. And he basically discovered that and published a book on how if you made processing coal more efficient, all of a sudden you'd have more and more coal plants, right? So what's been happening to us in computing, we understand this because we live this change, elastic demand, that increasing computing power efficiency has been radically increasing the amount of power that's consumed by computing. And there's various energy forecasts out there that are pretty scary. The interesting thing is that the hyperscale, green one at the bottom there is growing very, very fast. And then you should be worried also about things like networking, things like 5G that are purported to give us all these wonderful services are also driving a dramatic and radical increase in the amount of power consumed by computing and ICT. So none of us are against efficiency, but the point is that this fundamental dynamic means that power consumption is likely to continue to increase. Therefore, we still need to find ways to eliminate carbon footprint, even if power consumption is increasing. So how do we solve this serious carbon emissions problem for computing? Well, for a long time, people have been proposing good ideas. They're proposing this idea of load shifting or follow the sun, run from the carbon. run from the moon, I think I've heard it called, and other kinds of things. And that reflects this idea as illustrated by this plot on the left, that over the course of a day, the amount of renewables in a power grid can vary widely. So this is a plot taken from the California ISO, the California Power Grid, and you can see very clearly the solar trend, this green line, where it increases at the beginning of the sun coming up and then falls sharply at the bottom. You'll also notice, if you look at this carefully, that this orange line represents natural gas, and the natural gas generation actually accounts for more of the power for all of the non-daylight hours and grows dramatically right towards the end of the day, fueling air conditioning and other kinds of things. So if you have these kinds of structures, and they're different in every grid around the world, in fact, you can compute from that some kind of notion of what is the CO2 per unit power that's being emitted, as shown by this blue line. And then you could imagine modulating your data center load according to this gray line to increase it when there's low carbon energy available. So the idea is to do arbitrage over these carbon emissions. And this is actually a good idea. But these techniques are limited by the dynamic range of these data centers. And of course, the swings of these carbon emissions. And these ideas were proposed nearly 20 years ago, right, when the internet was really taking off, when the cloud was small, or these data centers were small. And so the problem is the cloud is big now. So when you shift this power, you actually move the dispatch of the grid because the power, it can be as much as 6% in some grids today. It's over 2% national in the United States, and it's the single fastest growing consumer of power in the power grid. So the problem is that shifting moves changes the power grid dispatch. So you really want to think about something called marginal carbon. And we recently published a paper that shows actually the problems that shifting can cause. And this graph is intended to show basically that even though you shift power according to this average carbon, you may not get what you would expect. So, it's a complicated graph, but if you think about it, what you'd like to do is increase load, that is move from the center to the right and have no increase in carbon, right? But when you decrease the load, decrease the carbon. And it turns out that if you do these grid simulations properly, in many cases, you actually don't do the right thing and you are not able to reduce the carbon in the grid. But I encourage you to dig down in this paper. The point is that these data center loads are large enough that they're actually affecting what's going on in the grid, so they can't easily use these simple average measures. If you were to study the power grid for a while, and we work with folks that spend their whole lives studying the power grid, they would tell you that the challenge is that you really need to think about marginal carbon. So marginal is the term the economists use, right? It's change one unit here, what changes in the system. Engineers would call this, what is the derivative of the carbon with respect to load? So decarbon, deload, right? So most people naively think that as I increase the power, carbon emissions go up in some quasi-linear fashion. But actually, the power grid is a lot more complicated than that. And what actually happens is, as different sources are actually brought onto the grid, the carbon emissions go up in this complicated way, right? Sometimes steeply, sometimes flat, sometimes close to flat. So it turns out that when you consume power, where you consume power, if your consumption is predictable, if your consumption is regular, all affect, in a complicated way, what your carbon impact actually is, right? And you have to model the grid in a complicated way, actually, to capture this kind of knowledge. So I would argue that we've been living in a world where we think about this naively in the computing community. And we're also, it's not just the computing community, maybe much of the world has been thinking about this naively. And that means that we've been living in a world that I'll call good, better, best, right? So what the cloud companies have done, many of them buying offsets and calling themselves carbon neutral, right? Google, for example, has been claiming it's carbon neutral since 2007. And by this definition, they are. The idea is that they have some power use, as shown here on the left, and they buy a block of renewable generation, and they say, over the year, I offset this thing. So it's an offsetting approach, just like you can buy trees to offset your air flights, right? But that's good. It's not a bad thing. It's done good things, created a lot of renewable generation. However, it is a long ways from actually eliminating your carbon footprint. A better approach would be to do what Google has now committed itself to do, 24/7 matching, which is something that they've promised to do by 2030. And their goal is there's this data center use, which I've drawn in brown here. And the idea is they're going to buy enough renewable energy that they're going to cover all of that brown stuff by 2030, right? And in all of their geographies, right? Now, first, not all of the cloud companies have committed to doing this. And second, Google has only promised to do this by 2030. And the Google CEO, Sundar Pichai, said publicly, we don't know how to do this, right? And it might actually cost us money. So I don't know, right? So that's the problem, right? So they're actually starting to have to think about solving some hard problems and starting to pay money for this. And some of the other companies have not even signed up to do this. No need to name them. What I propose is that we really should have the ambition as the computing community to do what I would call best, right? That is, we need to create computing as a flexible load. And, we lay that challenge out. We've been pushing this since 2015, but really commercial companies have started to do this at some scale, say around 2018. And the idea behind this is that what we want to do is we want to flex the computing load. Oops, what happened here? Flex the computing load up to match renewable availability. So what we want to do is we want to increase the load when there's actually renewables available. And then we want to flex load down, right, to when renewables are not available. So we want to match renewable availability. So we're always actually consuming renewable energy, of course, but also we're helping the grid absorb renewable energy, right? And then, of course, there's going to have to be some kind of reliable floor to make most of our cloud style systems work. So the challenge is, and I hope that you guys can get inspired to take this ambitious goal that we should pursue best for computing technology so that computing can truly be, right, an unalloyed good for sustainability. So computing infrastructure can and should eliminate its negative carbon impact, but we can do more actually than the half steps and the small steps that the cloud companies have been proposing, and that computing infrastructure should be a part of the solution for this problem of carbon emissions in the electrical system, not just neutralizing its own negative effects, right? So you might ask the question, well, what is possible? I keep hearing, from these cloud companies, they can't do this, they can't do that, it costs real money, right? So in order to figure out what was possible, we started a project many years ago called Zero Carbon Cloud. And the idea of Zero Carbon Cloud is to do computing on stranded power. It turns out that there's excess renewable power in the grid, and it's growing rapidly, and I'll talk more about that in a minute, that is going to waste. That excess renewable power is zero marginal carbon power. That is, if you increase consumption at the right times, at the right locations, there's no increase in carbon associated with that consumption of power. So in effect, Zero Carbon Cloud has this idea of taking data centers, right? So we have traditional data centers and they live in this reliable power abstraction. You've got the power grid, which creates reliable power from renewable generation and other kinds of generation. And the idea of Zero Carbon Cloud is we should take some computing facilities and put them on the unreliable side of the power grid. And they should be dispatchable loads, and this should allow us actually to do very useful computing with zero marginal carbon and reduce the carbon impact of computing, but also increase the effectiveness of the grid in absorbing renewables. So the challenge is, right, how much of this can we do? And of course, we're eliminating scope 2 carbon emissions, if that terminology is familiar to you. So first, a little bit of a tutorial on how the power grid works, because this is, of course, the computing community. The way the modern power grid works is that it has to deal with very, very dynamic generation and load. Renewables are by definition unreliable generators, right? So the way that this problem has been solved is through something called a power market. And there's a continuous bidding in 24-hour, 5-minute kind of intervals of offers of power that come from these different kinds of generators. These offers come into a power grid market, which then uses something called economic dispatch, typically lowest cost power first, to decide who actually is going to be used in the operation of the power grid. Now, interestingly, what happens in this is very often the market determines that certain kinds of power won't get used. And it can determine this for cost reasons. It can determine this for transmission limitation reasons. It can determine this for load fluctuation reasons. And when that happens, right, it tells a whole bunch of these renewable sources, no, you're not allowed to put your renewable generation into the grid. So that power gets wasted. So this problem is in some sense easy to solve at the 10 or 20% kind of renewables that many of our power grids operate at in the US. It becomes quite difficult around 33%, and California is starting to have radical problems. Parts of the Midwest are starting to have radical problems. It's very difficult at 50%. And it's an unsolved problem, both economically and technically, as you get into 50, 60, 70 kind of percent kinds of numbers. So the problem is that this is creating in our power grids renewable excesses that are large and growing, and that generation excess leads to curtailment, waste, and this negative pricing. Because negative pricing is a natural result in a market when you have oversupply. What does this actually look like? Andrew, you're telling us that power is actually being dumped in the power grid. Really? Turns out it's true. We started doing this analysis, and this is, what it looks like to a generation site in the Midwest. This generation site, this data is taken from January or April of 2015. And what this plot shows is along the x-axis, the number of megawatts in a particular 5-minute interval that this generator offered to the power grid. And what's shown on the y-axis is how many megawatts it was allowed to put into the power grid for that 5-minute interval. And so if you're thinking about this, what you'd realize is that in a perfect world for the generator, all these dots would be on this diagonal line, right? I'd always offer, say, 20 megawatts, and I'd be allowed to put 20 megawatts in it. Yeah. And what's happening is all of these dots in this lower triangle represent curtailment. That is the ability to generate power that was not allowed into the grid and therefore dumped and wasted. So this is happening a lot. So this is sort of a microscopic view of one generator, probably a pretty unhappy generator. But if you look at a couple of things, the first is that these quantities of power are quite large. So the number of megawatts here is 10, 20, 30, 40, this is 110 or 20 megawatt generation. And the amount of energy being curtailed, as you can see from down here, is often 60, 70, 80 megawatts. So we're pretty proud of ourselves. We think our data center loads are really big, and they are growing to be quite large. But 40 megawatts used to be a pretty good sized data center. 80 megawatts is a pretty good sized data center. This is one wind farm, right? Unable to put 80 or 100 megawatts into the power grid. Now, if you look at whole power grids, you find these numbers are truly large. So ERCOT is the Texas power grid that famously failed in the winter of this year. And if we studied the ERCOT power grid, we looked at this curtailment phenomena. And if you combine various kinds of negative price power with this curtailment, as much as 20 terawatt hours of energy are being wasted on an annual basis. And you can see the steady growth, right, of this power consumption. And that really is terawatt hours, right? So we all know what tera means in the computing community, so I don't have to explain that. But you should be thinking that how many tens of thousands of gigawatts, right, gigawatt hours are actually available that could be captured, right, if you could somehow capture this waste. It's not just Texas. California has this problem in spades. So this plot's a little bit more complicated. 2017 in blue, 2018 in dark blue, 2019 in yellow, 2020 in this kind of dark maroon, right? And you can see steadily, right, monthly curtailment increasing on an annual basis. I spent a year embedded at CAISO so I could analyze this data, and we were able to show that there was a 40% compound annual growth rate in this curtailed power. And actually, what I suspect, no way to confirm this, I suspect one of the reasons they're reporting this now is I wrote a bunch of internal reports and they said, we better start disclosing this to our regulators or we're going to get in trouble. So there's now a number of terawatt hours, right, that are being wasted in this way. And California has growing renewables that are just going to drive this chart through the sky over the next 5 years. If you look globally, so if you look nationwide, there's a company that started to exploit this called Lancium, and they created some charts that show what negative pricing frequency looks like sort of on a national scale. And you can see that it's correlated with various kinds of renewable generation and growing in frequency, right? If I showed you the 2017, 2018, 2019 plots, this is the 2020 plot, and it's concentrated in regions with large renewable supply and limited transmission, and is just growing at an accelerating rate. So in these dark blue areas, over 20% of the time there's negative pricing, And other times, even more than that, there's curtailment in these power grids. So we started thinking about this question of, okay, there's all this excess energy around. Could you actually use it? And it turned out that no one had actually tried to figure out if you could use it. And the reason for that is that the power grid folks view this as waste. It's like wasted heat energy or something like that. And they assumed that it was so small and so irregular that nobody could use it. But we actually studied the MISO power grid, and we published some analysis that characterizes the temporal and spatial structure of this power. And it turns out that this stranded power is usable and exists in long intervals. So if you look at this chart, what it shows is that if you use the right power acquisition model, that you can achieve duty factors of as high as 70 or 80%. That's what our study showed. And the contribution of that 70, 80% availability is tied to durations of more than 100 hours, that's the red shown, more than 10 hours, that's the brown shown, and then more than 1 to 10 hours, more than 1 hour in the yellow. So the most of it is not like flickering on and off, it's like on for an hour, on for 10 hours, on for 100 hours. And that's pretty usable for certain kinds of computing. Now, this Lancium company I mentioned earlier did a commercial study and began quoting actually proposed contracts to potential customers, a distribution that looks like this, which is slightly different from the distribution I showed you at the left, but captures the same idea, which is a large amount of the duty factors coming from more than 96 hours, more than 48 hours, and more than 24 hours, really quite usable power capability for all kinds of computing. So surprising, right? So this power exists in large quantity and it exists in a usable form. So we set off to characterize, could you actually make a good computing system out of this? So I spend a day a week out at Argonne. Argonne has a number of large supercomputers. So we were able to get large scale scientific computing batch workloads for Argonne and ask the question, well, if I put up a system that had this traditional reliably powered computing facility, and then I paired it with a zero carbon cloud system of equal size, and I powered that one with this stranded renewable power, what kind of performance could I get? And, we basically looked and compared things like turnaround time, right? The amount of time it takes for your batch job to get scheduled and run, and total cost of ownership. And what we found actually was pretty remarkable. It turns out that the hybrid system has user turnaround time that's statistically identical to the reliable system. Let me say that again. This performance, right, the effective quality of service achieved for users of this hybrid system was just as good as if all of the system had reliably powered resources, right? So why is that? Well, it turns out that the variability of the power supply, right, is noise actually compared to the variability of the batch scheduling delays that these scientific users are seeing. So if that's true, then there's the opportunity to eliminate nearly half of the carbon footprint of these scientific computing systems by simply partitioning them in this way and operating them with the zero carbon cloud discipline. And if you take this idea to its natural conclusion, it turns out that because you can eliminate the power costs, because you can build cheaper facilities by doing this, that you can actually build much, much larger computing facilities, the thing that the scientific computing folks want, which is as big a computer as possible, if you can pursue this kind of an approach, right? So this graph down here below shows that as the consumption of these scientific computing systems, as their power consumption grows, the number of peak petaflops per $1 million of TCO that you would require actually to buy and operate these systems is such that if you did it only with reliable power, that it would grow as these blue bars show. And if you did it in this hybrid fashion with partially, this stranded renewable power, that you could actually grow the capacity of the system dramatically. And you could have 80% higher peak throughput by 2027, which at the time we wrote this paper was 10 years away, but now it's just, 5 or 6 years away. So you could have 80% higher peak throughput because you have this much, much bigger system. You're able to take some of those power dollars and turn them into buying more hardware. And that system has 45% higher throughput for your scientific workloads, right? So it's both more scalable and higher effective capacity, despite the intermittence of the power. It turns out if you apply this kind of TCO analysis to data centers, right, using both academic TCO models, that's what Viral here is, or widely used industrial rules of thumb, that's what the Hamilton with 3-year hardware upgrades and Hamilton with 5-year upgrades show. What you can see is that for many systems in the United States, right, under those TCO models, it's actually possible to achieve systems that have higher throughput per $1 million of TCO, $1 million per year of TCO. And that's shown in the light green and the dark green bars. They're systems for the same cost that are delivering higher throughput. Of course, the US has relatively cheap power. If you go to places where power is more expensive, like say Japan or Germany, actually the advantages are much, much larger. So if you can actually have a flexible workload, because these systems have some capacity that's fluctuating with the available of this stranded renewable power, these systems in aggregate can already be cost effective, and even more so in regions with high power costs. So we're beginning to see some acknowledgement of that and adoption of these ideas. So it is possible technically to do more, and all of the power consumed by these zero carbon cloud approaches actually help the grid decarbonize, because they're actually helping the grid absorb more of this excess renewable power, right? So I think that you can all imagine different ways that we can broaden this model, right? Because the cloud is really in its infancy in adopting flexible models, flexible deployment, dynamic resource management, and so on. But sometimes we get pushback on this when we talk about this, and people say, why ask so much of computing, right? Computing, the climate's not that serious, and computing is a small part of it. Aren't good and better enough? And our response to them is, computing is significant, has a significantly negative impact on the grid, even if we claim it's we're doing nothing. So we did a simulation of a bunch of different scenarios for the power grid, and looking at adding more data centers and also looking at increasing renewables over time. So what we have here on this plot is growing wind penetration in a power grid, and then different scenarios for 0 data centers, 10, 20, 30, 40 data centers, right? And as you add these as a constant load, what happens to the achieved grid renewable absorption, so-called RPS, as shown as the vertical axis? Well, it turns out that the system with no data centers in it has the best renewable absorption. And as you add data centers, the renewable absorption gets worse and worse. And I'll explain why that is in a minute. But basically, the notion that even if you take reliable, stable computing load and add it to the grid, it by itself is making this problem harder and making the grid work harder to actually achieve high renewable absorption. So in this scenario, the growth of data centers reduces grid absorption of renewables by 1.5 to 5% due to load misalignment. Okay. So these results were recently published in the ACM conference on e-energy in June of this year. So you might look at this and say, suppose I believe that's true. What's actually going on? Well, here's the intuition for what's going on. The intuition is, and I showed you this plot before, over the course of the day, the renewable generation varies, right? So the California power grid has a 2 times daily swing in carbon content, as shown here, right? And when I add data center load that is just constant over the course of the day, it actually pulls the RPS down. So it pulls the RPS down because that load is constant, but the renewables are only available for maybe 1/3 of the day. 33% renewable availability would be typical for solar or wind. So you got increased consumption in the 2/3 of the day when renewables are not available, or the 2/3 of the year when the renewables are not available. So adding data center load is pulling this RPS down. So basically you're acting as a drag, or you're retarding actually progress towards high renewable grids. So I think it's not fair to say that computing is not responsible for this rapid growth in power consumption, right? So that's the first, complaint we get. The second, pushback we get is, oh, well, I'm working on efficiency. Doesn't efficiency solve the problem? Well, efficiency is great. I mean, no one's against efficiency, and all of the advances in efficiency are good things, right, for trying to reduce the carbon, footprint of computing. But you heard the Jevons paradox story earlier. And this is just a plot that shows Google's power consumption. And Google has been very good about reporting this. So I don't want to beat up on them for the fact that they report this, but the trends in the power they're consuming show this rapid growth. And if you look at recent publications that analyze the generation, analyze the consumption, right, of power by the hyperscalers, right? So the Googles and Apples and Facebooks and Amazons and Microsofts of the world, that power consumption is growing the fastest as the part of data centers. So here's the data from that Massenet 2020 paper. Here's extrapolation based on renewable purchases. And there, if you continue at a 30% CAGR rate, which is what fits the trend line, we're looking at potentially very, very large continued growth in power consumption from the hyperscalers. So efficiency doesn't seem to be solving the problem. We really need to do more. So what more can we do? Well, if you build on this idea of zero carbon cloud, the basic notion here is that if we're going to help the grid decarbonize, if we're going to do better, right, then what the grid needs is flexible loads, right? So essentially what the power grid needs is there's times when the power grid has a surplus of renewable power, and it really wants to ask computing facilities, IoT, maybe buildings, can you increase the load now? Because really that would help us absorb more renewable power. And the absorption of that renewable power, would have probably zero or close to zero incremental carbon impact, incremental carbon emissions impact. And then there's other times when there's maybe not enough renewable power or not much renewable power, where the grid would really like to ask everyone to decrease their load, right? So this notion of a flexible load, right, is the key idea here, right? So of course, load shifting was chasing this kind of an idea. That was, against a static backdrop of a power grid, but now we have this dynamic backdrop of a power grid, right? So that's a challenge. So the upside of all this computing growth, I like to try and turn lemon into lemonade, right? Lemons into lemonade, right? Or to make a silk purse out of a sow's ear, computing power growth is growing dramatically. So the upside of it is, hey, we're not so tiny anymore. We're big enough to actually help the power grid now. And we're going to be bigger in the future, so we'll be able to help the power grid more. So the more dynamic range that we can create for power consumption, the more leverage that we can have. So to pursue this idea of a flexible load or a dispatchable load, we actually studied, right, zero carbon cloud a number of years ago and looked at different scenarios for how to add load to the grid. So this study back in 2016, when we did this work, showed that if you add data centers as a dispatchable load, it can make as much of a 7% difference in their impact on achieved RPS relative to other ways of adding that load to the grid that are not so flexible and not so dispatchable. In the grid simulation we did here, this corresponded to an RPS increased renewable absorption of really 18 terawatt hours. And you can on your own time compute how many sort of metric tons of CO2 that would correspond to, even in a highly renewable grid. So how you integrate these loads into the grid make a big difference for how much impact they have on the grid's ability to achieve decarbonization. So recently, we did another study that looks at different ways that the data centers could negotiate how they do their flexing relative to the grid. And I don't have time to sort of explain this big complicated graph, but this study used a realistic mix of data centers and growing renewables. The data center load was similar to the North Virginia mix, right? So if you know about data center deployments, you know that there's a huge concentration of data centers in Northern Virginia. And we looked at two strategies. One is data center driven, the cloud companies deciding how to modulate their load. And the second was grid control driven, that is the power grid, dictating to the data centers how their load was going to vary over the course of the day and the week and so on. And this plot on the right shows that at high renewable penetration grids, that in fact, giving the grid control over a large scale of dynamic range can actually make a huge difference. It can achieve as much as a 1.6% increase in the grid RPS that's achieved. Whereas giving the data centers control and allowing them to do selfish local optimization, in this case for power and renewable fraction, produces a much smaller benefit, perhaps only half as big in terms of achieving grid decarbonization. So that's shown in the striped green bar here. And then, the error bars, right, are shown with these whisker plots because these are statistical simulations over statistical generation, statistical use, and statistical load. So the results are, it turns out that if you actually allow these grids to modulate the flex in the data center load, they can actually eliminate most of the negative impact I talked about before. So if the data centers were willing to do this, and that's a big if, right, they could actually eliminate their negative impact on the power grid. Okay, so I promised to tell you a little bit about how this is happening in reality. So we had this crazy idea in a little room at the University of Chicago in 2015, and we wrote a few papers about it, and then we started to develop these ideas. And then in 2018, a bunch of intrepid entrepreneurs, Michael McNamara, showed up on my doorstep here in Chicago, and they said, we've been talking to people about this idea, and they keep saying, you should go talk to Andrew Chien. He's published a bunch of papers on this idea, zero carbon cloud. So Michael started a company called Lancium, and he's been driving this idea. They sell something they call pausable computing. And this is the first deployed system that they built in 2020. I'll call it phase 0, which was demonstration scale. And you can see it's a bunch of these lightweight data centers. It's a few megawatts, right? And it's operating literally in the shadow, right, of these wind farms, right? And its features are a bunch of, container-based data centers and a huge power distribution, right, structure right behind it. So that was 2020, and things have been racing along. And it turns out that just about 3 weeks ago, Lancium broke ground on their clean campus at Fort Stockton, Texas, happening inside the ERCOT power grid. And the phase 1 for that facility is 300 megawatts. And they expect to fully populate 300 megawatts by the end of 2022. And then they're going to go on to the next 300 megawatts. That resource will be utilized in these growing low and negative pricing periods. And the availability is good and increasing, as we've talked about, 90, 95%, and so on. The power cost is low and decreasing. And it turns out, because they're able to help the power grid, they actually are selling ancillary services into the power grid as well. So in addition to delivering computing, they're getting paid on the backside by the power grid for helping to solve the power grid's problems. They sent me a picture because I act as an advisor for them. So they sent me a picture about this. This is what their facility looks like today. So here, just a couple of weeks later, right, you can see they've already put up a fairly large physical infrastructure. And you can see that there is a large quantity of these step-down transformers that allow them to connect to the power grid and connect, something like 300 megawatts, right? These rather unassuming sheds, they're far less fancy than you might think of a Google data center or an Amazon data center and so on. And that's because they're hyper cost engineered for low cost and slightly less reliability. And if you read, the business literature that Lancium produces, they're arguing that their TCO can be as much as 2x lower, right, than these marquee, high cost, highly reliable, 5.9 kinds of data centers. So these ideas are gaining some traction, and I think this is by far not the last facility that will be built this way. I think that you'll see gigawatts of construction on this in the next 5 years. Okay, so you've heard me talk about this idea of good, better, and best. Good, we've been seeing cloud companies do for over a decade. Better, we're starting to see people talk about this ambition of 24/7 matching, but they're really not there yet. And it is a hard goal. And we should applaud the companies that are doing this. We should encourage the companies that have not yet committed to this. And we should help them by creating technologies that help them achieve these goals. But really, computing should have a higher ambition. So computing should really have the ambition of enabling grid decarbonization. We need to create technologies that allow computing to flex load up to match renewable availability and accelerate the decarbonization of the power grid, and thereby accelerate the decarbonization, the true decarbonization of computing, and make it an unalloyed good for sustainability. Okay, so large-scale shifting and flexibility can both drive down carbon emissions for compute and also help the grid. I don't know why it says grid, help the grid decarbonize. Maybe that's twice as good. So what more do we need? Or maybe how can I help, right? So, if IC2E is a community of advanced, sophisticated researchers creating technology, how can the IC2E community help with this ambitious challenge? Well, there's lots of challenges in cloud systems and applications. There's lots of research needs. The fundamental need here is to increase load flexibility. We've spent the last 20 years of the cloud focusing on increasing reliability. And in fact, doing just the opposite of increasing load flexibility, because there's been a huge push towards predictability and fill these data centers with nary a gap in them, this TCO optimization. But now we actually need system software to create and exploit flexibility. And that includes new resource abstractions, new cloud resource management. I'll talk about this Challenger variable capacity, and new capability to exploit dynamic information to make these systems kinds of decisions, right? And so that's super important at the platform level. And there's lots of interesting challenges there. It's also super important at the applications level. So I've been really pleased over the last 2 years. I've been getting lots of inflow from developers that are all saying, how can I do something? How can I build a carbon aware application? How can I reduce the carbon footprint of the software I'm building, and so on? So it's really gratifying to hear the kind of energized enthusiasm that there is. So I think we're going to see carbon aware applications that are going to adapt the signals, right? Carbon signals to shift load in time and space. And they're going to do this, in some progression of more intelligent, more sophisticated, more statistical and logistical kinds of changes over time. And frankly, they're going to do this without regard for the infrastructure providers. So the infrastructure providers better get ready and support this. And the applications folks ought to chase after this, because this is the leverage we have to move these big, slow moving infrastructures, right? So in order to do all of this, of course, we need information, right? So the grid is complicated, carbon emissions are complicated. We need new information services to project key power grid state and future state, right? To enable computing to make good decisions. And of course, we need information services that inform us, but we also need information services that insulate us from the complexity of the power grid, because we've got enough to do on the computing side. We don't want to all become simulators of the power grid, right? So I'll talk about that. So first, let me talk about this idea of resource management for variable capacity, because we've been trying to energize the community to study this new and challenging problem. So if you look at the power grid's carbon emission rate in a pretty advanced power grid, German power grid, you'll see that over the different months of the year, you get radically different emissions, right, for 1 megawatt hour of computing. And it varies over the time of day. These are sample days. It varies over the year, right? If you were to do what I think is a reasonable thing to do, is instead of running your data center as always full on, you gave yourself a constant budget for carbon emissions. So I'm going to run my data center at a more aggressive goal, right? When a higher power level, right? When carbon is low, and I'm going to run it at a lower power level when carbon is high. So here's a sample of what you might get for a day chosen out of one of these months. I actually don't even remember which month it is, varying over the course of the day. So it might be 200 megawatts at a particular early point in the day. It might be 100 megawatts later in the day. We don't build resource managers that are designed to deal with this kind of variable capacity. Google has announced recently a new carbon aware effort, and it produces a small variation in capacity. I think we're going to see a large variation in capacity. The example shown here is as much as 50% over the course of the day. So there's lots of interesting questions about how do we do resource management effectively, and how do we create load flexibility to allow us to make good use of this. And this could come from carbon, it could come from peak charges, it could come from fluctuations in load, and many other causes. So there's this whole interesting question of what does the variation look like, and how do I even get started? So in order to help the community get started, we published a structured framework that formulates this problem. We published a bunch of traces, right, that expose power, carbon emission variation, price variation, different other metrics, right, that could produce variation, and traces that would allow people to do studies. So if you're interested in this problem, I encourage you to go look at all of this information that's available on our web pages and linked to this publication that should be available, right, since July of this year. Now, it's not just carbon that is increasingly volatile. It turns out that these power markets are going a bit crazy with respect to price as well, and it reflects this changing sort of generation mix. So if you look at power price over the course of the day, here's a sample day for the mid-continent ISO power grid, you can see that actually there's spiking going on, and those spikes can be quite large. The peak here to the lowest ratio is something like 7 or 8-fold, right? And if you were to just do price optimization for your data center, power price optimization, and vary your capacity based on power price optimization, you would see a different shape, but no less volatile a capacity. So we think that this is broadly a really challenging sort of resource management challenge, and we encourage folks to look at what we published and hopefully advance it and work on this problem as a way of helping the grid become more flexible. So that's one problem, variable capacity resource management. A second problem is, how do you get information? You know, if you're a computing person, how do you get information to make good decisions about the right place, and the right time to do computing, right? So, you know, we started a project called RIP-IT, right place, right time. Apologies for the acronym. We like it, but it's a kind of a hard challenge to get an acronym for right place, right time. And the basic idea is the place that the RIP-IT carbon emission service lives is to interpret the complex dynamic behavior of the grid and expose that information in terms of, you know, carbon emissions, real-time telemetry, as well as forecasts to data centers or other kinds of loads that might choose to adapt their behavior. So the idea here is to make this variable carbon emissions landscape much simpler to deal with and enable the computing infrastructure to make intelligent decisions to reduce the carbon emissions, to help enable the CI to make decisions to help the power grid absorb more renewables, and of course, enable the computing infrastructure to reduce its power costs. And I should say this is a joint effort with Lene Verwalt at the University of Wisconsin, who's a power grid expert, and with Rich Wolski at UCSB, who of course is a cloud computing expert. Conceptually, the way you might think about this is that, you know, the complex wind variation and load variation are coming together in this power grid market. So as all that stuff comes together, you have to take forecasts of all of those things and put them together to plan what the power grid is going to do and to estimate what the carbon emissions profile might look like, both over the course of a day or over the course of a year, right, and in different seasons. So the ambition for this RIP-IT carbon metric service, and we just put up a starter website, so you can click on this link when you get a minute and go look at what we're starting to do and what we hope to do over the next couple of quarters, has the ambition of presenting this information in a fashion that makes it actionable for computing services. And that not only means accuracy, but it also means in a structure and with a set of APIs to make it easy for computing devices and computing workloads to actually do sensible things relative to carbon emissions implied in the power grid. So those are two things on the systems research side, and there's many, many more, and I'd be happy to talk about those in questions or offline. But there's also a challenge for computer architecture, and I hope we have some computer architects in the audience. So the problem is that one of the things we run up against constantly is from cloud engineers who have said, look, you know, data center headroom is really expensive. Our whole goal is to keep the data centers full. And we do a lot of cloud hardware engineering for TCO. And the optimization point is full utilization. But the problem is, right, that view of full utilization is a narrow, fixed target and doesn't have any regard for all these other operating points. And the design flexibility that's possible is really much larger, as you saw from that example of the Lancium facility. So the challenge for the computer architecture community is to break out of this notion of thinking about PUE as a single value. That PUE really can and should vary with capacity, as should TCO. TCO should vary with capacity. And we should create data centers that have a high dynamic range that dynamically are cost effective, not just optimized for a single operating point. And that means we should build facilities that have headrooms of 25%, 50%, maybe even 100%. And they should have high dynamic range across these facilities. So what does that actually mean? I wanted to show you a picture to conceptualize it. So Andre Barroso and Urs Hölzle famously published a paper many, many years ago, I'm sure you've all seen, about this idea of energy proportionality. And the idea was, as I increased load or increased capacity, that I would have a straight line in terms of energy proportional computing. And this also turns out to be, these systems are optimized for PUE right here at the top of this range, right? Power use efficiency. What I'd encourage you to think about is we should build systems that actually have dynamic range above that, right? So that's heretical. First, let's break out of the box, right? Let's have headroom. Let's have 50% excess capacity, right? And when I'm using that excess capacity, I'm going to use it to exploit excess renewables, which means that the power may be close to zero cost, and the power may have zero implied carbon emissions. So I shouldn't feel bad about having a low PUE. So out here, maybe it's okay for PUE to increase, right? And that's curve to be steeper, right? And that's really what's going on in these kinds of cost engineered facilities like, we proposed in Zero Carbon Cloud and Lancium is building. So I think there's lots of opportunities to do this. There's exciting things like immersion cooling happening that should allow us to do this in this context with negative cost power. Okay, one more a slide to just impress upon you the urgency of this. I put together the RPS goals for a bunch of municipalities that have advertised such things. So on this chart, across this period from 2020 up to 2050, here are the goals for California, New York. New York's remarkably progressive. A lot of people don't know that. Massachusetts, Germany, Spain, and overall EU to decarbonize their power grids. These are radical goals, right? I mean, you're talking about going from 10, 20, 30, 40% to doubling that in nearly all cases in just the next 10 years, and then going, to even higher levels, right, by 2050. In grids that are going to achieve these goals based on renewable generation, what you're going to see is massive excess renewables, massive fluctuations that grow in proportion to the amount of renewable generation in the grid. And the simple way that you can see this is that these renewables typically are 33% capacity factor. So that means that if you have an RPS goal of 25, 50, 75%, or even 100%, you've got to build generation plants that is a multiple of that by 3. Right? So, even to get to 50%, you're going to have peak generation. That's 150% of the average load in your power grid. So the point is that necessarily this kind of aggressive decarbonization of the power grid is going to increase this fluctuation and the many opportunities around this stranded renewable power. So with that, good, better, best, let's drive and demand that the computing community aspire to best and accelerate the decarbonization of the power grid. And it's not something for the power engineers to solve. It's not something for the economists to solve. This is something that you can help solve. So think about system research opportunities that can help us decarbonize the power grid, and think about architecture research opportunities. And I hope that you'll dig in and learn about this and get excited about it. Thank you for your attention. I'd be happy to field any questions.
Thank you so much, Andrew. That was fantastic. Really fantastic work. If you have a question, I'd be happy to take them either through chat, or you can just unmute yourself and ask your question as you're getting ready to do that. I would like to start by asking Andrew about the investment that's happening in infrastructure in the US, and if that is going to translate at all to the updating or upgrading of our power grid. And if so, how is it going to be used to address this inability to absorb renewables? And my second part of that question is, if we can be involved with that infrastructure update, how would you want it changed to enable some of these ideas that you're pursuing here?
It's a great question. So, of course, as we speak, people on Capitol Hill in the United States are negotiating what could or could not be right in such packages. But generally speaking, the more the things that are driving more aggressive adoption of renewable energy, the power grid, transmission updates and infrastructure updates and those kinds of policies are all generally things that we need, right, to move to a higher renewable fraction. It's a mistake to think those investments will solve this problem. They will come nowhere close to solving this problem. They're so far behind the curve in catching up to this kind of stuff that these problems are not going away. A couple things. Really hard to get transmission line built, takes decades, right? And we can prove that it's not economically feasible to build enough transmission to solve these problems. Simple argument, fluctuating need for that transmission, if it's 10% of the time, if it's 20% of the time, it's 30% of the time, probably doesn't make sense to build that thing because the thing you're transmitting across at first has almost zero value, right? And it only shows up 10 or 20 or 30% of the time. So very, very hard to justify the building of all those things. In fact, I think what fundamentally underlies this radical transformation to renewable energy is a shift away from the notion that every megawatt hour should be carefully husbanded and make sure that we put it to good use. Wasting energy is bad is a mantra we've had for decades. In fact, I think in this new world, lots of energy is going to be wasted. And what's exciting to me is how do we exploit more opportunities where there's just these big pools of wasted energy, right? And we go and exploit them. Unless you think that a little bit crazy, I get calls from VCs, like literally every month with other crazy ideas, like, green hydrogen, right? Like biofuels, like all kinds, lightweight manufacturing, nitrogen fixing for fertilizer, all based on this emerging large-scale stranded power that everyone sees is coming and they see no way that we can avoid having it. So think about good ways to use it. Don't think about it's going to go away, right?
Great points. Alex, do you want to unmute yourself and ask your question? Alex asking Andrew in the chat about flexible pricing and using batteries.
Good.
Where are we there, and what does that look like?
So batteries are a good thing. Energy storage is a good thing. The main problems with energy storage is that it's too expensive. The quantities of power that we're talking about, terawatt hours, right, gigawatt hours, and so on, are so large, right, that I once did a calculation to see what it would take to do the daily balancing for the CalISO power grid if I just bought an energy storage, and the conclusion was that it was at least double the power. The price of power would have to double in order to support those batteries. But battery companies that operate batteries want to make a profit, so probably it's triple, right? So the problem is that the economics of shifting this power in time using storage don't work yet, right? And as renewables increase, right, you're chasing this larger and larger thing and declining economic benefits. So it gets harder and harder. So I think it's unlikely energy storage will ever solve all of this problem, right? So there's going to be this excess power. At the same time, energy storage is tremendously helpful for helping the power grid do regulation and other kinds of things. So I think you're going to see more and more energy storage on the grid. It's just not going to be big enough to solve these problems at the scale we're talking about. It only can be large enough in countries that are lucky enough to have many mountains and reservoirs. And like Switzerland or Sweden or a few countries are lucky to do that. But in the United States, for example, we don't have the geography to have enough energy storage to solve these problems. And we're not the only country that has that challenge.
Excellent. Any other questions from our audience?
Yeah, I put up this long list of papers, not so much to expect you to read it, but it'll get into the video and then people can look at it later if they want
That's a great idea.
to dig things up. Yeah.
Perfect. I'm going to stop the recording.